In this video, we'll introduce the idea of learning word representations. In the previous video, we introduced the notion of one-hot encoding or one-hot representation, which allows us to get a vectorial representation out of a word. And the way we do that is that we just create a vector filled with zeros of size corresponding number of words in our vocabulary, and then we put a single one at the position associated with the ID of a word. And if we have a sequence of words, we can concatenate these one-hot vectors, and this way we can get a vectorial representation that is more amenable to machine learning and particular usage, for instance, in a neural network. Now, unfortunately, this vector is going to be very high dimensional, and there are consequences associated with that. In particular, we're more vulnerable to overfitting because we're in much higher dimensions, so we're going to have many more parameters to train, so we'll need more data for that. There might also be some problems computationally with manipulating such vectors for certain operations. So now what we'll see in this video, we'll introduce this fundamental idea that I've been introducing in the context of neural networks for tackling as an alternative to using the one-hot encoding, and which works really well in practice. So the idea is that instead of using this fixed representation that makes no assumption about the similarity of words, we're instead going to try to learn a representation, a vector representation for words directly, which is going to hopefully model the similarity, syntactic and semantic, between the words. So what we'll do is that for each word, we'll learn some sort of mapping that takes the word ID and then maps it into a representation CW, which is going to be, in this case, a vector. So for instance, this is just a made-up example, but for the word the, say it has the ID 1, then CW might give us this vector, and then for a similar word, which would have, in this example, the ID 2, then it might give us a very similar vector where we see that the values in the vectors are actually quite similar. So the squared distance, Euclidean distance between the two vectors would be small. And then again, in this made-up example, having B would have a similar vector representation, cat and dog, and so on. And so the idea here we're introducing is this idea we'll try to learn what these vectors are. And ideally, we want to learn a representation which maintains similarity that's syntactic and semantic between the words. And as we'll see, it's going to be possible to do that inside of the neural network. So here's an example of some word representations that were learned with some given algorithm by Blitzer et al. In 2004. So I'm showing this figure here because it really illustrates well this what we're trying to accomplish here. So the word representations that they learned, if they were projected in 2 dimensions, they were able to learn representations such that all the months were associated with a vector in 2D, which was in the same region of the 2D space. Here it learned all the different numbers. Here it had million and billion. All the days of the week were all around the same position, again, in the 2D space. So that's what we're trying to achieve, and trying to find a way of actually learning this vectorial space for the different words. So for now, just imagine we actually had these word representations, then we could use them instead of the one-hot encoding to create the vectorial representations of a sequence of words that we could feed to a neural network. So if we had a problem where we wanted to make a prediction based on a window of 10 words, so W1 up to W10, then similarly as with the one-hot encodings, we could just concatenate the learned word representation. So we take CW1 and then concatenate it with CW2, CW3 up to CW10, and then we'll use that as our input representation X, and then we could feed that to the neural network. Now the question is, how do we actually learn this mapping, these vectors for all the different words in our vocabulary? Well, the idea is that we actually use gradient descent, and the way we're going to do that is that we're going to treat these word representations as parameters inside the neural network, parameters that the neural network, when we are performing backpropagation, will be able to train when we do stochastic gradient descent. So we won't only update the neural network parameters, we'll also update the vectors in our vector space. So each representation CW that is in some given input, X, is going to be updated by taking its current value and then subtracting a step size or learning rate times the gradient of whatever loss we're optimizing in our neural network with respect to that vector that is at the input of the neural network. And that will give us a new representation which we can use next time we use the word W as input to a neural net. And so instead of just doing stochastic gradient descent on the parameters of the neural network, the idea here is that to learn the word representations, we'll also do gradient descent on the word representation themselves. So to sum up the procedure for learning these word representations, we would first initialize all the word vectors randomly in some way, much like the parameters of the neural network. And then every time we would feed a representation as part of the input of the neural net, then during backpropagation, we would backpropagate the gradient towards the word representation, and then we would update the word representation also based on the standard stochastic gradient descent rule. And so as the neural network trains, it will not only adapt its connections, its hidden units, and its output units to perform the task better, it will also adapt the word representation themselves so that it's better able to learn the task that it has to solve. So we'll often represent all of these word representations and store them into a matrix, which I'm calling C here in bold. And essentially, the rows of that matrix will correspond to the word representation CW. Now, one thing we can notice is that obtaining CW, so for a word ID W, obtaining the word representation, if it's stored in a matrix C, actually just corresponds to taking the one-hot vector of that word W and multiplying it on the left of the matrix by the matrix C. So if you think about it, if you take a vector filled with zeros and a single one in some position, and you multiply that by a matrix on its left, then the result is going to be the row of the matrix at the position where we put a 1 in the one-hot vector. And so another way of viewing this operation of taking a word ID and providing a word representation, a vector, is that we're actually taking the original one-hot encoding representation of the word and we're projecting it on the columns of W. And in other words, we're actually doing some sort of dimensionality reduction, reducing the dimensionality of the original one-hot or one-hot representation of the words into a lower dimensions or lower dimensional space, which is going to be such that we're less likely to overfit, for instance. And that's something we haven't mentioned thus far, but actually the size of the word representations is something that we can choose. It's going to actually be treated as a hyperparameter, much like the hidden units of the neural network. And also, if you view this process of providing a word representation for a word W as just this linear transformation, then it becomes more obvious why it is that we can actually propagate gradients and train this matrix C. It's just a linear transformation of some original vector representation of the words. And much like the other matrix multiplications we do in the neural net, we have no difficulty backpropagating gradients through these vector multiplications. Now, that being said, this is mainly conceptual. That is, when we implement taking a word ID W and providing a vector CW, we really implement it as a lookup table and not as an expensive multiplication of a vector that's mostly zeros with a matrix. Specifically, one way of doing that is that CW would just return an array that points to the wth row of the matrix C. So that's the main idea for learning word representations. And in the following videos, we'll see different approaches that use this idea for solving natural language processing tasks. And the first one that we'll see is language modeling task. And it's in that context that word representations have been first introduced. So in that context, it will become, I think, much more concrete what we mean by word representations.